Okay, my name is Uwe Fritsche. Welcome, hello. Thanks for inviting me to give a brief talk about an issue which is worth to talk about for at least a week. I'll be trying to compress some of the discussions in a few slides. I'm a physicist. I worked for about 28 years at Öko Institute. Some of you know this institution based in Germany. Since April this year, I'm leading a new small group, which is the International Institute for Sustainability Analysis and Strategy, a transdisciplinary think tank. Half of our staff is not in Germany. So what I'm going to do is to talk a little bit about the land use change associated with biomass. But the principle is also, you can transfer it to non-biogenic options if you have extraction of ores or something. But I won't talk about that because from the order of magnitude impact, the biomass is the most relevant one. To introduce the thing, direct land use change is something which is easy to understand because we can observe it. We can go out into the field and measure what is the change in the above ground, that's where the plants are, and the below ground, that's where the roots and the carbon in the soil is. How does it change when we change the use of the land? For example, when we say there was a forest or there was a bushland, and then we clear that and bring in something else to have feedstocks for anything. So we know from the IPCC, which has worked on that since the early 1990s already, last century, on the direct land use change issues. We have regional default data and so forth. That's a reasonable approach to go ahead. What's important to understand is a lot of people think direct land use change is always bad. No, that's not true. In a lot of cases, it is negative. That means there's a release of carbon, which is then oxidized to carbon dioxide, a greenhouse warming impact. But there are also cases where direct land use change is positive, where you improve the carbon balance both above and below ground. So there are some options for that, and if you're interested, we can talk about that later. So we understand this part of the land use very well, I would say. And this is not, again, as I said, it's not only for biomass cultivation, it's also for other land-using activities. We had an intense debate about tar sands, for example, in Canada, on their footprint in terms of land use change when they clear forests to extract tar. But it compares, because of the land intensity of biomass, pretty much by an order of 3 orders of magnitude more for biomass systems. But there might be exceptions. Now, the indirect part, that's where the fun is and a lot of myth, a lot of magic is in the room. Because something which is indirect is not easy to catch. And actually, physically, it doesn't exist. Why do we have indirect land use change? Well, we will come to that. That's an issue of system boundaries. But it's easy to understand if you look to the direct impacts in your life cycle. So you have the cultivation stage and you clear something. But there was a use of the land before. And this use might be still needed. There's still demand, for example, for food you have grown on that land. So you will crowd out or displace the previous use, and this previous use might move to somewhere else, and somewhere else you will have direct land use change. And this direct land use change could, in some cases, occur on high carbon stock land. And then you would have a greenhouse gas release somewhere else, outside of the system boundaries of your life cycle. But you can calculate that and you can attribute it, allocate it to the, in this case, bioenergy or other biomass feedstock production. That's the logic behind it. To put that in an equation, don't get excited about it. It's easy to understand. It's really simple math. You have a certain amount of carbon, might be a forest before you change the land use. Then you have a certain amount of carbon after the land use. And then you have a certain amount of why you had the land use. You get something out of this land use. And you distribute the total changes in carbon over a certain amount of time. Because this is you might say in simplified terms, this is a one-time poof where you release a lot of carbon within a few years, but your product might live and your cultivation might live for many years. So you have to kind of distribute this. And people have agreed that a distribution of about 20, in some cases 25, or some countries use 30 years, but a few decades are easy. Now, this approach can be easily translated to any feedstocks. It was developed for bioenergy. It's a Renewable Energy Directive, which is a law in Europe, which governs the way we calculate greenhouse gas emissions from biofuels and liquid bioenergy. But we can easily replace, it's a simple transformation to take out the megajoules and put in tons or kilograms or pounds or whatever, a mass unit, and then you get the same for the release of greenhouse gases, direct land use change, from products which are not measured in energy. And as indirect land use change is just direct land use change happening somewhere else, this is the same equation which is used to calculate indirect effects. The only question we have is how do they relate? So to quantify the direct land use change is easy, more or less, if you know where and what. It's not that complicated. You can do it for any material you take out of the cultivation. Again, just to visualize what does it mean when we talk about indirect land use change, assume that in the middle, in the center of this graph, you have a given amount of land which is used currently for food or feed production. It could also be timber or pulp and paper or raw materials for resins, whatever, something useful. And now you enter to have a new biomass plantation, which has not the same use than before. So you displace some of that, and because there is still a demand, you would have a market reaction requiring that somewhere else on this planet, or maybe even outside of the planet if you have a very high value product, you would try to get a replacement. And this would be either if you move into a forest area or savannas or something, then you have high carbon impacts. If you move into some wetlands or something, you might have lower figures, or if you move into something which is or underused, you might have even possibly negative. That means a reduction of carbon. It depends on where you go. And that's where then, if you make it easy, we have a four-step calculation. Again, it's not that you typically do it on a per unit base, even if the life cycle logic and the product carbon footprint is typically on a unit base. Typically, we want to look into systems because it's not happening that you have 1 hectare or 1 kilogram, but you have a certain policy to increase a certain amount of, in this case, for example, biofuels. That's where most of the models have been run. You define a business as usual case. You then assume that there is a certain shock, an instantaneous change in the demand, that you say a policy which rewards biofuels or a quota system or whatever brings up, for example, 1 million tons of oil equivalents more, and then you calculate how much land do you use to produce this biofuel or other bioenergy carrier or biomaterial, doesn't matter. And then you have to determine how much of that displaces existing production. And this is, first of all, an economic question. Once you've resolved that, the next step is, again, straightforward. You look, where did this indirect land use change occur? This is also more or less an economic issue. Do you have infrastructure to go into savanna or grasslands, or are you allowed to clear forests? Can you move into peatlands? Is there available land on that and infrastructure and so forth? And once you have done that, you know the carbon signature of these changes, and then you can translate it into either megajoules or any other measure or metrics you want to use. Just to indicate, no numbers, if you're happy, you can take all this, ordinate and so forth. But the idea behind this graph is just to show you there are a couple of biofuels out there which are existing commodities, nothing magic behind them. Biodiesel from various resources, ethanol from sugarcane, ethanol from grains of various sorts. And you see that a couple of studies which have been, this is only a compilation from the last 2 years, if we can make about 100 studies from the last 10 years on that, you see that there is an order of magnitude appearing, with some significant exceptions, which gives you a range of the greenhouse gas in CO2 equivalents per megajoule of biofuels delivered between the different groups of biofuels. That's all I want to say. And the biggest... Oh, sorry, sugar ethanol, sugar cane ethanol, sorry. It's a weak contrast. You know. And the important thing here is to understand that we can say certain commodities which are translated into biofuels can be associated with a certain land use type and also with a change of land use type. And this is a regional thing. And in that sense, we can identify pretty well what the, if we take these results, we can translate that from the energy world, from the biofuels world, into any biomass commodity on this planet.
I have a detailed question, but maybe it's relevant to the previous. Can I go?
Please go ahead.
Yeah, because do I understand it right that your axis, let's say, is around 60 grams CO2 per megajoule? I know the value for natural gas, it's 56.
Yeah.
So does that mean that this is really contributing more to the planet if it's higher than 56 than natural gas does?
Absolutely.
Okay, thank you.
The comparator for fossil liquid fuels in Europe is 84 grams per megajoule of CO2 equivalent. So you see that there are some which contribute to a reduction, but there are some which significantly increase if you take into account the indirect land use change and other life cycles and so forth. And that's what I'm saying on the next part. I just wanted to say there is also there's a different methodology people have used. We have contributed to the development of that, which gives you an ILOC factor, which you can translate not to an energy flow or mass flow, but you can translate into a hectare-based figure, and that's much easier because in some cases you don't know exactly where what will be grown. We heard it in the case of Colombia. There might be confidentiality issues and so forth, or there might be just uncertainty because you don't know in 10 years from now where your feedstock will come from. So we made a proxy in a minimum figure, which is not a maximum. Maximum would be 5 times higher, but this is a minimum figure. So if you are uncertain about the potential indirect land use change impact from your commodity from the cultivation stage, you can use a 3.5 tons per CO2 equivalent per hectare. And you have your cheese footprint, milk footprint, meat footprint. All these food and feed related activities should consider, and also timber, should consider these kind of things. We also say, because of some of the understanding of the certainty in a broader sense, we should disaggregate the result and should say, well, if there is a direct land use change, it should be visible. If there is an indirect land use change assumed, it should also be visible and should be kept separate. So that people can say, oh, I doubt this ILO concept, or it might be mitigated in the future, or I have compensation for it, or whatever. There are many policies which you can deal with ILOC. So in that sense, it's not enough to quantify it and put it into one aggregate number of the greenhouse gas signature. It should be disaggregated. Last but not least, and this is a message I would like to underline very much, even if it's beyond what we're talking about, if we have a policy regime as the United Nations Framework Convention on Climate Change, which is by definition comprehensive enough to have the widest system boundaries, the Earth, with all its atmosphere, all its soils, all the carbon anywhere, then we could put a cap, a global cap, on the carbon, which we haven't yet done, and we could do that for all sectors. That means including forestry, including agriculture, including anything. And then we wouldn't have any displacement anymore because everything would be accounted for, everything would be under the cap, and there wouldn't be any indirect effect anymore. But unless we have that, we have leakage. We have this effect that outside of the system where we look and regulate, something happens. And it might be bigger than the impact we look into, and that's why we have to take care of that. So if you want to read a little bit more, there are a couple of studies which focus the European situation. The IEA publication focus the global situation. And send me an email if you want to have some of the references. I'm happy to distribute that. And I want to underline that the EU is getting ready. It's now since about 2 years, but this time we believe they really will deliver on having a proposal on how to deal with indirect land use change for carbon emissions of the biofuels debate. We expect it next or the week after in October. Thank you for your interest.